So you may have looked at the last videos there on our derivative with the limit process and said, boy, that seems a little involved. What if the function gets really, really difficult? Or what if we just don't want to go through all that hassle to find this slope of the line? Is there an easier way? Well, yes, actually there is one that we could use depending on how we want to do it. And in this case, what we're actually after is we're after looking at a function right here in which we might be interested in saying, well, all right, what would be the slope, the equation of the line tangent to the point of f at 2, 5, right? We went through and we found an equation in the last one. So let's go through and figure this one out right here. There's 2, 5, right? We want to say, well, okay, what's the equation of the line tangent to the curve at that point? Well, one way of dealing with this is what is called this alternate definition. And essentially the way this definition works, it's slightly different than our last one. It's like this. It says, well, all right, if we're interested in a line that is actually tangent to the curve, like a little nicer line to deal with right here, and I didn't want to find that whole x minus h business, I could actually just do it with the point that I already know and say, all right, let's pick some point c away, right, at f of c, some other point. And right here, oops, let me get my pen going. Right here is where that second point is. Oh, gosh. So we're interested in finding the value of the point. Well, let's pick some other point, c, right? So x minus c. Well, our point c right here, we're going to say c is 2, right? So at c equals 2, right? At c equals 2, we find some other point right here at x f of x, whatever the value of x is. And let's let that value of x just simply approach c, which kind of makes sense. I mean, rather than saying, okay, some distance away, h away, well, look, f of c is a fixed point, right? C, f of c is 2, so f of c is 5. So all we would really have to do in this process is say, well, all right, at c equals 2, we're going to say f of c is equal to 5, because f of 2 is equal to 5. And let's make the substitution into this expression. So our limit right here, as x approaches 2, is going to be f of x, which is x squared plus 1 minus 5, all divided by x minus 2. And let's see what happens, right? We take our function, we subtract the y value at the point we're interested in, and divide it by our point. The limit as x approaches 2 of x squared minus 4 divided by x minus 2 is certainly one we can evaluate because we've done this before. This is like saying we're going to take the limit as x approaches 2 of x plus 2 times x minus 2 divided by x minus 2, and we note that x minus 2 cancels out, so we're just taking the limit as x approaches 2 of x plus 2, and as x approaches 2 of x plus 2, we substitute and we get 4. And so this is the slope that we want. And so building the equation of the line is actually no big deal, right? We know that the formula y minus y1 is equal to m times x minus x1 is a useful one if we're building the equation of a line given a point and the slope, which we have. We have y minus 5 is equal to our slope of 4 times x minus 2, which is our x value at our point, which becomes y minus 5 equals 4x minus 8. Adding 5 to both sides produces y is equal to 4x minus 3. And so it turns out that the line that we're actually interested in, our tangent line, will have a slope. I'm just going to go to my line here. Will have a slope. Nice color here. We'll have a slope of 4 and pass through the point in -3. Y equals 4x minus 3. That's our line right there. Okay, so not too bad.